So let's get to the major issue, which is this one. Okay, so this is the major issue, and as I mentioned, it's a major issue because this number L, which you're trying to find, the exponent for the smallest power of 2, which is 1 mod n, in itself could be thousands of digits. I mean, it turns out it'll be less than n, capital N, the number you're trying to factor, but n is could be as large as 10 to the 1,000 if there are 1,000-digit numbers. So if you just try it by doing a for loop where you're like, all right, I'll try 2 to the power 1, 2 to the power 2, 2 to the power 3, like we did by hand, I'll just say this is a bad idea, would be to say, all right, I'll say L is 1, V is 2, and then we'll do loop until V equals 1. And here we'll increment L, and we'll do V equals, I'm going to write this, times 2 mod, I ran out of space here, mod n V. Okay, this is a correct algorithm for implementing step 1. This is my a little shorthand little subfunction that you give it a number v and it just multiplies it by 2 and takes it mod n. So basically, this algorithm just doubles v mod n. But this is a very bad idea because it just counts up until it finds the first L, and if the first L is a 1,000-digit number, then its magnitude is 10 to the 1,000, and 10 to the 1,000 is far more than the number of whatever attoseconds in the lifetime of the universe. So you'll never get there. And might be a little bit funny, but let me draw a picture of this bad idea algorithm failing to work, because it'll illustrate a point. In some weird way, this algorithm is also an algorithm that's searching a graph. So it might sound funny, but it's the case. Let's even think of a little graph here where the nodes are labeled by numbers mod n. So, there's 1. And then if you double it, mod n, then you get to 2. Okay? And then if you double that, mod n, you get to 4. If you double that, mod n, you get to 8. Okay? And, well, you can keep going. At the beginning, it'll look like powers of 2. But, if there's 1,000-digit numbers, then after maybe 1,000 steps or so, or maybe 3,000 steps or so, it'll start wrapping around. And after that, it'll just kind of, to you, if you were to draw this, just look like kind of random numbers. So let me do an example where, n is 1,003. This is still a terrible and misleading example because the number of digits is 4, and we should think of the number of digits as being 1,000. But I cannot do any examples with more than 4 digits. Okay, so you're going along, you get to 512 maybe. And then, as I said, finally it'll wrap around because 2 times this is a 1024, which is the same as 21. Okay, and then I guess it'll still look like doubling to the untrained eye for a while, 42. But it's going to start wrapping around lots of times. This is all, mod n. And it'll eventually get to, well, actually, you tell me. What will this be? It's small enough, the numbers, that you can do it in your head. Yeah? Yes, 502. You'd be 502, and then you'll be wait a minute, 502. If I double that, I get 1,004, which is 1 mod n. Okay, so I guess that actually means this will be 250. Hey, this will be 251. How cool. Neat. Yeah. So, well, I cannot ask you to do in your head, how many steps did that take, because that's a big calculation. But I can just tell you, this turned out to be 2 to the power of 232 mod n. And I would actually say here you got pretty lucky because 232 is merely 1/4 of n. It could have been twice as long or even longer. But you see, L itself is going to be a huge number, of comparable magnitude to n. So you don't want to try to like walk all the way around this circle with this algorithm until you like luckily hit 1. Ideally, you would prefer to do something faster. Okay. Actually, I made you do this little calculation about 502. We can ask ourselves the following question. Obviously, you could start making this graph. It's always nice to make a graph in any computer science problem. And start at 1 and keep applying this operation, double or times 2 mod n. And it's clear that that takes you to 2, and then to 4, and then to 8, so that every vertex, okay, so this graph I claim is a directed cycle, And part of this is every vertex has out degree 1. And, from doing times 2, mod n. But I claim also every vertex has in degree 1 as well. I'll ask you, why is this the case? Okay, if you keep making this graph, I claim that actually any vertex you have can only have, it has exactly one predecessor. So why is that? Or you could say to yourself, how do I get to the predecessor? Like what little routine should I do in my head to figure out the predecessor of a number? Yeah? That's correct. What was said was if it's even, you divide by 2. And if it's odd, then you add n and divide by 2. That's right. I'll make it a little harder then. Suppose we were doing a base other than 2. So this was like, let's say the base was 3. So this was like 1, 3, 9, 27, ... something. How do you go back? Yeah? N is not even. That's a good question. N is p times q, and p and q are odd primes. So it's this would go wrong if n were even. Yeah. It will also go wrong if the base is not, in general, doesn't make GCD 1 with n. But here we're only doing the base being 2, and n is not even. Yeah. Yeah, that's right. That's what I'm going for. You can divide by 2 mod n as well. I mean, you can definitely multiply by 2 mod n, but you can also divide by 2 mod n whenever n is even. And that's what's going on here. So I could say you could do from doing, you might say times half mod n. And this is like a tiny bit of number theory, I guess I should say. Here, when I write half, I mean like mod n. So that means the number, which if you multiply by that number and then multiply by 2, it cancels out. So it's in this case, here a half is 501. Okay, because it means if you do like 2 times x, and then you do like 501 times that, 502, sorry. 502. You get like 1024 times x, but that's 1 times x mod, I'm doing everything wrong here. 1004. That's 1 times x mod 1003. Okay, so when you do mod 1003, the opposite of doubling is multiplying by 502. Because if you double and then you multiply by 502, it like cancels out, or vice versa. And whenever n is odd, which it is, there will always be some number which is like multiplying by it is like the opposite of doubling. In fact, it's easy to figure out what it is. It's just half of 1 plus this number. Now, more generally, if you're using a different base, you have to figure out, like, if you're using base like 5, you have to figure out what is 1/5 mod n. But there's a little number theory for that. But when it's 2, it's easy. Okay, so every number has like, well, you can, go forward by doing times 2 mod n. And you can also go backwards from every number by doing times, you might call it a half, or in this case, specific case, it's times 502. That's for going back. Okay, so if you make this graph, like every vertex has out degree 1, every vertex has in degree 1, so the only graph that's like that is like a directed cycle. Yeah? Very good. Yeah. So let me in fact say that now. This cycle will not contain all of the numbers mod n. In fact, it'll contain some, I don't want to say random, but like some weird, subcollection of the numbers. In fact, it'll contain exactly L numbers, whatever L turns out to be. And we saw that, I don't know, we did this example where, n was 21 and L turned out to be 6. So this cycle will only have 6 things on it. Now, actually, here we started at 1 and we kept doing times 2 and we argued that because every vertex has out degree 1 and in degree 1. If you just keep going for a while, you eventually have to hit 1 again. But that won't use up all the numbers. So you could start at like any unused number and also make a cycle out of it and make a cycle out of it. And there'd be like one where you start at 0, you just get a self loop where you keep going to 0. So actually, using times 2 mod n and times a half mod n, this will break up all the numbers mod n into a bunch of directed cycles of different lengths. But we're only going to care about the cycle that contains 1. And what we're really going to be obsessed with is how long is that cycle. Okay, so really, this is a good point. Let me write it as a summary. That's fine. Okay, so this is a summary. Given n, the powers of 2 mod n form a set, which I'll call, I don't know, S. In this case, S has 232 elements. Okay, and these S has L elements, which we can naturally arrange on this cycle. And to factor n, we need to find L, or want to find L. Okay, so there's a little bit of a psychological thing here. Whatever capital N is, this cycle exists, and it has some set S of all the numbers mod n in it. And maybe there's L of them. So this cycle, which includes 1 that you get by just doubling, has some length L. That exists. But the algorithm doesn't know what L is when it's given n. And that's actually the whole goal. Given n, it's I got to figure out how long this cycle is. And the length of this cycle is 10 to the 1,000 or something probably. So it's longer than the number of atoms in the universe or whatever. So it could just literally walk along the whole cycle until it gets back to the beginning and be all right, I found the length. But that's a terrible idea. So somehow, using the power of quantum computing, we want to really speed up this step 1. Now, let's see. We have efficient code, classical code, for doing times 2 mod n. It's really almost extremely simple. It's literally left shift by 1 bit. That's the times 2 part. But then you got mod n. That's the annoying part. But OK, there's simple code for this. And this has a property that it cyclically, one might say, permutes the elements of S. So if you think of just these numbers and this list as like a set, and this times 2 mod n, it's the tiny subroutine, like permutes them. Like 1 maps to 2, 2 maps to 4, 4 maps to 8, 21 maps to 42 in this example, and so forth. Moreover, we also have the inverse permutation, which is times a half mod n for the inverse permutation. Okay, so we can make some efficient code that, you give it 42 and it outputs 21, and you give it 21 and it outputs 512, and so forth. Okay, and that's just, in this particular case, multiplying by 502. So actually, what I'm getting at here is, if you're trying to factor n, some giant number, you can write down, pretty simple code that doubles numbers mod n. You can also, on the side, figure out what is a half mod n. Actually, that's very easy. It's just n plus 1 divided by 2. And you can write another piece of code that does times that number mod n, just times 502 mod n. And so now you have code for a permutation of these numbers and also for the inverse permutation of these numbers. So now, you surely don't remember all the way back to lecture 6 and homework 3, but in the privacy of your own home, you can remember back to those days when we were talking about if I give you classical code, what does it mean to make quantum version of the code? And if there were several cases where if you have classical code and it outputs 1 bit, you could have the quantum version could be if that code then toggle A, or if that code then minus. And if it outputted, the classical code outputted multiple bits, you could have if that code then toggle these bunch of bits. But we also threw in there, even though we never really used it, if you have code that happens to do a permutation of some bit strings, so this code is classically reversible, and the code for the reverse, then that code is doing something which is eligible to just be a straight-up quantum subroutine. If you have a classically reversible function, that's eligible to be a quantum subroutine on qubits. And moreover, if you know the code, the classical code for doing this permutation, and also the code for doing this inverse, then it was a homework problem, how to convert it to quantum code for doing this instruction. So the summary here is, hence, by some stuff we did on homework 3 and so forth, we can convert the code for this and the code for this into a quantum code. And it's about the same number of instructions, so it's also efficient. We can get efficient quantum code that does the classical reversible operation times 2 mod n on qubits. So in particular, on elements of S encoded with, qubits. Okay, so just to clarify what I mean by that, I have this handy example here. This is actually from the example where n is 21. And this little picture, so when n is 21, you're okay, 21, that's a number that I need 5 bits to store it, because it's less than 32. So all your computations only need 5 bits. And like this is a picture actually of this self-same circle. Because like in base 2, I think you guys can do this. This is like 1, 2, 4, 8, 16. 2 times 16 is 32, which is 11 mod 21. And this is 11. And then we double this again, we get 22, which is 1 mod 1. Okay, so if you started with like 5 bits written like this, and you kept doing the classical algorithm times 2 mod 21 on them, like it would go tick, 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 and then back here. And what I'm saying is, like, we now can get like a quantum subroutine with like, toggles and if-thens and so forth. That is a property that when you give it like qubits in this like 5-qubit basic state, and then you run the code, like it'll take it to this basic state, then this one, then this one, this one, this one, and then back to this one. Moreover, it was pointed out that like you could also run this code on like a number that doesn't appear in this cycle, like 3. And like it would actually still do, it's still like reversible there too, so it would go like 3, 6, it's still doubling, so it'll go 3, 6, 12, 24 is the same as 3. So it goes like 3, 6, 12, 3, 6, 12, 3, 6, 12. So it actually would break up all the numbers mod 21 into like a bunch of cycles. We're only going to care about the cycle, again, that contains the basic state 1. But it is like globally, classically reversible on all the numbers mod 21. And maybe you can cook it up so that like for numbers that are bigger than 21, it just like returns this itself. So like if you give it the binary encoding, of some number that's bigger than 21, because you have to have this because there's like 5 bits, then you can just define that like it first checks to see that, and then it just returns the number itself or something. Okay, so this is like a critical first step, which will help us do the first key step, the major issue of like determining L. Okay? Basically, the unitary for this times 2 mod n operation is the unitary that is the adjacency matrix of this directed cycle. It really says like how times 2 mod n forms like a directed cycle. And using this, we want to try to figure out what L is.